In this part of the lecture, we will consider spectra of alkali metals. Well, spectra of alkali metals resembles spectra of hydrogen with some differences. And if we look at the periodic table, we see that alkali metals are in the first group, in the same where hydrogen is. And they have one electron, they have valence of 1, and they have one electron, which is in the outer shell of atom. So the structure of these atoms resembles that of structure of hydrogen. As we observe in alkali metals several series, and the series resemble series of hydrogen, and they are called also as a sharp, principal, diffuse, and fundamental. And sharp, as I already explained you, is because it is sharp, diffuse because it is diffuse, and principal is called because it is observed both in emission and in absorption. And fundamental was called fundamental because of its similarity to the corresponding lines of hydrogen. If we compare empirical formulas for alkali metals with empirical formulas for frequencies which are emitted by hydrogen, I just remind you that for hydrogen we have, for example, for general case, omega nm is Rydberg constant, and here is 1 over m squared minus 1 over n squared. And if we denote this r multiplied by 1 over m squared as omega infinity, because when n goes to infinity, so this term goes to 0, so the only remaining term is r divided by m squared. So in the case, this is in the case of hydrogen, and in the case of alkali metal, corresponding formula is similar, but a little bit more complex. We have omega is equal to omega infinity minus Rydberg constant divided by n plus alpha squared. Here again, omega infinity corresponds to the limit of the series, and n is integer number, and alpha is a fraction number. This constants, omega infinity and alpha, they have different values for different atoms, but different alkali metals. And for example, for S series, for sharp series, we have omega. We will denote this omega infinity for sharp series as S infinity, and minus r, and here n plus s small squared, where n is 4, 5, and so on. In this case, S, which stands for this alpha, is minus 135. For this is sharp. For principal, we have, okay, this is sharp, this is principal, then omega is, we will denote a limit frequency as p omega, minus r, and here n plus p small squared, and n starts from 3, 4, and so on, and p is minus 0.87. Next is diffuse, and here omega is g infinity minus constant Rydberg constant, and n plus g squared, and here n starts also from 3, 4, etc., and g is minus 0.01. And fundamental for fundamental omega is f infinity minus Rydberg's constant divided by n plus f squared, and here also n starts from 4, and f is 0. You see that what I said, that fundamental is called because of its similarity to hydrogen. If f is 0, so r divided by n squared, so it is similar to the case of hydrogen. Empirically was established that p infinity is equal to 3s. And what is this 3s? Okay, we will denote this term, we will denote it as ns, where n is this number. Look, ns does not mean that n is multiplied by s. ns, this is some symbol. So ns, it is not multiplication, it is symbol. 3s means that this is r divided by 3 plus s, and it corresponds to this series, sharp series. For this is established for this correspondence. Next, it was established that s infinity is equal to g infinity, and it is equal to 3p, and f infinity was found to be equal to 3d. Also, this is this term, this is np, and so on. Now we can rewrite these formulas in the following way. Then we can say that s, for s we have omega is equal to 3p minus ns, where n goes from 4. For p we have omega is 3s minus np, where n starts from 3. For g we have omega is equal to 3p minus nd, where n starts also from 4. And for f we have omega is 3d minus nf, where n starts from 4. Look, we considered only 4 different series, but it doesn't mean that there are only 4 of them. There are many different series after f, and it is customary to denote other series simply alphabetically after f. So the first 4 are called with these letters because of some physical meaning, and rest of them are called simply alphabetically E, F, E, G, and so on, or G, 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 E, and so on. Well, this resembles formulas for, in case of hydrogen, for difference of different terms. So these are optical terms. You remember that the term T on N with accuracy of sign is equal to energy, is proportional to energy of the transfer of electron. In the case of alkali metals, as we already mentioned, all these transfers of electron between different states are transfers of optical or valence electron, which is outer electron in atom. There are also some more than one electron, but due to structure of atoms in these alkali metals, some optical electron, valence electron, is in the outer shell of atom. Now that we have these formulas, and they help us to understand what transfers of electron in atom occur, which corresponds to the emission of these frequencies. Well, let's try to draw a scheme of atom similar to that for hydrogen. Again, we will draw it in the same manner. So this is energy axis, and this corresponds to angular momenta. It is customary for one electron to denote angular momentum with S, P, D, F, and so on with small letters, and for many electron systems with capital ones. So here we need to denote, first of all, in the scheme, this is energy, and somewhere in ground state, the electron should occupy some energy state. And in case of alkali metal, this state is n equal to 3. This is for this specific case is for sodium, and in sodium we have here that n is equal to 3. Why it is not 1? The point is that lower levels, energy levels, are occupied by rest of electrons, not this outer electron, and there is such a rule, we will study it a little bit later, which forbids to occupy levels with, so there is some limit how many electrons can occupy one level. And it appears that in case of sodium, we have for this first level, which can be occupied by valence electron, is n equal to 3. So the levels with n equal to 1 and n equal to 2 are already occupied. Now this first column is L equal to 0, so here is L, so this is 0, and this corresponds to S. We denote it with S. So next is somewhere here, it is 4, then somewhere here is 5, 6, 7, and so on. Next is L equal to 1, and this corresponds to principal. Column, this is L is equal to 1. And distinct of hydrogen atom, in the case of sodium, this level, which has the same number 3, but a different P, has a different energy. So here is number 3 for P series. Also 4 is here, it is not the same as energy of this level is not the same as for S column, the same as for 5, 6, and so on. The next series is L equal to 2, here is D, and 4, it starts from, again, D can start from 3. You remember that L changes from 0 to n minus 1, and if D is 2, so 3 minus 1 is 2, so again it can be a number 3 somewhere here. It is again larger than this one. This is 3, 4, and so on. And finally, what we consider series F, 3, and for this column, we cannot start from 3 because n minus 1 is, in this case, if is 2, so we can start from 4. So the lowest level for this column is 4. So now we have all levels located on already here, and now we can look at how to put it in order to, I will check whether it is visible. Yes, it is. So now we can look what is happening. For series S, sharp series, we have transfers from 3p to ns. So this means that final state is 3p, this one, and transfers occur from ns, from this column. So we see that this corresponds to this gives us sharp. This is sharp series. Next is P, and P is fundamental. Sorry, principal, and as already mentioned, that principal means that it is observed both in emission and absorption. So the final state is 3s, this is final state, and transfers are from this, that, and so on. This is principal. Series, and indeed, as far as this is ground state, so if sodium atom absorb energy, it will change its state from this to some of neighboring column. You remember that there is a selection rule which forbids such transfers and transfers of such kind from this column, for example, to that column, because delta L should be 1. For next diffuse series, we have transfers to final state is 3p here, and from a D column. So this is diffuse. This is diffuse. And finally, this fundamental is here to 3D from NF, from different states in F column. So this is fundamental. What is specific and different from what we observed in case of hydrogen is that now E, energy of level, depends on L. So E depends now on two parameters, N and L. Consequently, we see that levels with the same number N have a different energy. It occurs because in the case of hydrogen, the field between the field which produced a force between a nucleus and electron was just a force produced by 2 point charges, and here a nucleus is screened with inner electrons, and so the potential in which this outer electron moves is more complicated. So depending of shape of this function, shape of function, I mean that probability to occupy different positions in a round atom, it appears that energy will be different because it is no longer in direction of point charges, but it is moving of one charge in more complicated potential. This is called that degeneracy on L is removed. Degeneracy, I would like to remind you that degeneracy means that a level is degenerate in case for the different states which are described by different wave function, we have the same energy. Here we see that when E is already depending both on LL, so this means that the degeneracy on L was removed. Now we will consider the rules for summation of angular momenta. Let's consider a system which consisted of two particles, and these particles have orbital or angular momenta L1 and L2. The problem is to find possible values for some summary moment, how these moments can be added in order to obtain the angular moment, total angular moment of the system consisted of two electrons, each of which have its own angular momentum. It is evident that this number L, this is momentum. Momentum L depends on the mutual direction of L1 and L2 as usual when two vectors are added. Also, it is evident that both this momentum and momentum L1 and L2 are quantized, so they can accept only some discrete values. We remember that it is possible to simultaneously measure the square of momentum, which is h squared L plus 1. In previous introduction of momentum, I denoted it by m, but here it is denoted by L, just to stress that this L, it is momentum, and it depends on quantum numbers, which are also L. So with this arrow, this is momentum itself, vector, and this is quantum number L. So L squared can be measured simultaneously with projection of Lz, which is h m L. Here L starts from 0, so it is 0 and so on, and ml is 0 plus minus 1 plus minus 2 and so on up to plus minus L. Here are numbers which define projections of momentum L on some axis Z. Now we wish to find some correspondence between quantum numbers L, ml, and quantum numbers L1, ml1, and L2, ml2. Let's consider projections of momenta on the axis Z. So we have somehow defined axis Z, for example, with the help of magnetic field. And in this case, this is, say, vector L1. We remember that we can define only one angle. So somehow it can look at a different direction, but if we look at these two vectors, L1 and L2, and these vectors have projections which goes here, and this projection L2 is H bar M L2, and this is H bar M L1, and when we obtain sum of these two vectors, we have vector which is H M L. When we sum these two vectors, we obtain this vector. So it is evident that maybe I made it too long. Okay, let's go this up to this. This is L. So this is H M L. I mean that according to this drawing, it is evident that H, this projection H M L, should be sum of projections M L1 plus H M L2. From this equation, it immediately follows that the quantum number ML is ML1 plus ml2. It is also natural that L is integer number, and the number value of this number depends on the mutual orientation of L1 and L2, and when we will obtain L maximum. L maximum will be in the case that it equal to L maximum. Look, L maximum will equivalent to ML maximum, because ML maximum is plus minus L. So L maximum is ML maximal, and on the other hand, ML is ML1 maximal plus ML2 maximal. But if we look at these projections, they obey the same rule, so they have different values starting from 0 to up to L1. So maximal, which is reached by M, is L1, and the same is for this, maximum is L2. So L maximum, we see that it is L1 plus L2. This case we can illustrate with this figure, that if we draw this picture with maximal projections, and maximum projections is when this angle is minimal, because the length is defined by vector itself. So then if we have minimal angle here, it is L1, and minimal angle for this, it is L2, this is L1, this is L2, and in this case we have this is H L2, this is H L1. I substituted here maximal value, which is L2, and this, which is L1, and the sum of them is this plus this is somewhere here. Indeed, it is then L and this L is projection is HL. So this is the case when in classical physics we have adding or summation of parallel vectors. Here you see that L and its projection cannot coincide in any case, because there is always some difference between L and its projection. L can never be against along Z axis. Indeed, look, maximal L, moment L here, is H square root of L plus 1. And maximum projection is LZ HML, where maximum is where ML is equal to L. So LZ is H maximum is HL. So if we compare these two equations, we have that this equation is always larger than this one. So these are momenta, and this this is momenta. And you see that this is quantum number L, and here is L squared plus 1. So L squared plus L. So this is always larger than that one. This means that never momentum can have the same value as its projection. Projection is always less than vector itself. So this means that a vector cannot be directed along the axis on which we find this projection. Okay, in the cases we obtained a maximum value, and if we consider the case when these vectors are oriented in or directed in a different direction, I mean one of them is in this direction, that L2 is in that direction. This is corresponding figure to explain what I mean. This is Z, and we assume that this is L1, this is momentum itself, this is L2 in this direction. So classical physics, it corresponds to antiparallel summation of antiparallel momenta, and if we find what we have as a sum of these vectors, this is okay, this is H L1, this is minus H L2, and this is HL. Then we see that minimal, L minimal, is L1 minus L2. Again, if we look what is L2, it is maximal value which can be accepted by ML, and L1 is maximum which can be accepted by ML1, this ML1 which corresponds to this, and in case they are in a positive direction, we have to subtract one from other. And in this figure we have L1 greater than L2. And what will happen if L2 is larger than L1? Then L will be minus, this vector. But as a matter of fact, it is not possible, because it has no physical meaning. By the way, this is vector L. And so minimal, L minimal is actually absolute value of this difference of these two numbers. Now what we have? We have that L maximum is L1 plus L2, and L minimum is L1 minus L2 absolute. So L can be changed from L1 minus L2 absolute to L1 plus L2. And it is also known that L is changing by 1. So L is step is 1. So all the values which can be accepted by L are as follows. L can be L1 plus L2, then L1 plus L2 minus 1, this was maximum value, and so on until L1 minus L2. This is a rule how we obtain L number, quantum number for angular momentum for a system of two particles which with angular momentum which are characterized by L1 quantum number and quantum number L2. In the case of alkali metals, If this valence electron is removed, so atom is ionized, then from experiment it follows that the angular momentum of the residual atom is equal to 0. So we can conclude that angular momentum of atom is equal to angular momentum of its valence electron. As far as in excitation and emission of light, all other electrons, not except for valence electron, do not change their energy, their state. The level scheme of atom is identical with level scheme of levels of electron in some potential, which is formed by nucleus surrounded by inner electrons. And again, in this case, as we already used it, the selection rule delta L is plus minus 1 is valid. Now we will consider Zeeman effect. And the Zeeman effect consists in a splitting of spectral lines in the magnetic field. For electron magnetic moment, we now have to remind what we know from electricity, course of electricity, when we denoted magnetic moment with P with indices M. Now, because P is used for different purposes, we will denote magnetic moment as mu. And magnetic moment of electron, now we will denote angular moment again with M. So mu, magnetic moment mu, is minus this ratio of E over 2me. Please look in electricity to this formula. This is mechanical moment, angular moment, and this is magnetic moment. In the system which we use now, here it should be multiplied by velocity of light, c. This is a system in which k is equal to 1, remember in the force, Coulomb force. This formula, we derive this formula considering a moving of electron along some orbit and considering a mechanical moment and mechanical and magnetic moment which looked in different directions. So this is this minus, and electron moved along this orbit. Now we know that there is no orbits in atom, so the question arises whether this formula is holds in the case of quantum mechanics. So we have to state that indeed, as it follows from experiment, this model with electron moving along orbit works in this case, even if there is no orbits, but the formula is the same. So the relation between mechanical moment and magnetic moment holds true. As far as we have additional, this magnetic moment associated with movement of electron. So in this case we have additional energy, and gained from electricity. We know that this additional energy U is this moment minus mu H, where H is magnetic strength of magnetic field, and this is multiplication scalar product of two vectors, so it is minus mu H cosine alpha, where alpha is angle between H and mu, and if H produced this field which gives us z-axis. So h coincides with z-axis. Actually, it defines this axis. So we have minus h mu h, where mu h is projection of magnetic moment on this direction of h or z. Now we know that mu, we can substitute what is m, and this is minus e over 2 m e c, and instead of m we will substitute its values. So 2 m e c h square root of l plus 1. This is what we have for momentum m. This is usually denoted as this term. This term is usually denoted as mu b and is called a Bohr's magneton. And then we have l plus 1, and this mu b is eh over 2 m e c, Bohr's magnitude in system, in corresponding system of units in which we use c here. Then the projection of mu h is minus e over 2 m e c mh, where mh is projection of mechanical moment on the same axis. And this projection is, so it is minus e over 2 m e c, and this projection is mh, or it is minus mu b m. Sorry, I have to charge my device. Now we can continue. Meanwhile, I wrote the rest of formulas, and let's look what happens. We obtained that mu h is minus mu magneton, Bohr's magneton m, where m is magnetic number, quantum number. And now we can substitute it here. That results in additional energy, which we denote this U as additional energy for the level, and it is minus h mu h. And substituting this for mu h, we have mu b h m. Now each level, which energy of which depends on n and l, is depending also on m. And m can have 2l plus 1 different values. Remember, from minus l with step 1 to 0, and from 0 with step 1 to l. Totally 2l plus 1 different possibilities to m. And this results in splitting of level. Look, if in initial situation without external field, we have two levels. One level is characterized with angular momentum L equal to 0 and another with L equal to 1. Then this level can have three different orientation of momentum, so projection which are characterized by m equal to minus 1, 0 and plus 1, and this only with m equal to 1, to 0, only one possibility. And transition of electron from this level to this level will produce a line with frequency omega 0, because difference of energy is h omega 0. The situation is different if magnetic field is applied to this atom because of this additional energy. The upper level will be split into three levels. One is m equal to 0, one m is equal to 1, and one m equal to minus 1. So if transition is from this to that, so again it is omega 0. If a transition of electron is from this level to that level, so the energy is greater and frequency is greater as well. If transition is from this level to this level, it is natural that frequency is lower. So this is with magnetic field. Let's consider a more complicated case when transition occurs between two levels. One of level has L equal to 2, corresponding M can have values -2, -1, 0, 1, plus 2, and lower level has L equal to 1 with M, which can be -1, 0, and +1. Then the upper level, this is split into 5 levels, 1, 2, 3, 4, 5. So this is 0, +1, +2, -1, +2, and lower level is split into 3 levels, 0, +1, -1. Now look, if transition is between -1 and -1, or 0 and 0 and 1 and 1, these distances are always the same because they depend on M, so delta E depends only on M. So they will produce the same frequency omega 0. If transitions are from this level -2 to -1, so the difference of M is by 1 lower. So the same is when transition is from -1 to 0 or from 0 to +1. So the observable frequencies will be omega 0 minus delta omega. And if transitions are from, say, 0 to -1, so it is energy is greater than for this case, the same is for 1 +1 to 0 and +2 to 1. So these three transitions gives us the same omega 0 plus delta omega, the same frequency. So we have a splitting of these levels and corresponding frequencies of observable light. Now we have to mention that delta M, for delta M is selection rule, delta M can change by 1 plus minus or not change at all, because if L is changed by 1, its projection cannot be changed greater than by 1. Now we also understand why this M number, M quantum number, is called magnetic, because it is responsible for behavior of energy levels of atom. In the case it is located in a magnetic field.